We've spent the last number of days talking about electric forces. Now, you guys know that a force, in any context, electricity or otherwise, is a push or a pull. In order to have a force, in order to have a push or pull, you need something to be pushed or pulled. You need an experiencer. Let's look at gravity for a second. There's the earth that causes gravity. I've got a board marker in my hand right now. That board marker experiences a force because it's pulled downward by the earth's gravity. But what if I take that board marker away? What if that experiencer isn't there? Well, there's no longer a force. There's nothing to be pulled on or to be pushed on. So there's no force there. But the earth hasn't disappeared, and the gravity caused by the earth hasn't disappeared. The curvature of space-time that causes gravity is still there. So how do we describe gravity when we don't have anything to experience a force? In other words, how do we describe gravity when there is no force present because we have no experiencer? Well, in Physics 20, we used a concept called a gravitational field. A gravitational field is this human-created concept that tells us that there is an influence surrounding the Earth, this influence of the Earth surrounding the Earth that is there regardless of whether or not we have something to experience that influence. In other words, regardless of whether we have a force or not. An electric field is analogous to that. An electric field is a region that surrounds something, a region of space in which an electric force, not gravity, could be experienced by an object with charge. Now, we're not suggesting that you necessarily have to have an object with charge experiencing a force. We're just saying that we could experience a force caused by this other charge. Let's go back to the Earth and the board marker for a second. Let's pretend the Earth is not a mass, but rather it's a big charge. Let's pretend the board marker is another charge, a smaller charge. The Earth causes something, this mysterious field. If I put the board marker in its in that field, then there will be a force. But if I take that board marker away, the thing that caused that force isn't gone. It's still there. That big charge that's like the Earth is still there. But there's no longer a force because there's nothing there to experience it. The field is the region that surrounds that charge where there would be a force if we put the board marker there. It's still there even if we don't put the board marker there. We're just saying that it's the region that would be there if we did, it's the region in which there would be a force if we put the charge or the board marker there. Now, what is it, do you think, that would cause something like that? What is it that would cause a region that could cause an electric force? It's going to be a charge, right? A positive charge, or for that matter, it could be a negative charge. But the bottom line is, an electric charge is what causes an electric field, just like a mass is what causes a gravitational field. Electric fields surround electric charges, positive and negative electric charges. Now, electric fields influence things. They influence other charges, just like gravitational fields influence masses in a particular direction. When I place a board marker in a gravitational field, it always falls downward. If I put a charged particle in an electric field, it may move outwards or it may move inwards, but it has a particular direction associated with it. Therefore, we call an electric field and a gravitational field, for that matter, both vector fields. They have both magnitude and direction. And that's opposed to things like light fields or heat fields that we would call scalar fields. The light above me on the ceiling influences me, but not in a particular direction. So that would be a scalar field. The heat coming from the radiator in the room influences me, but not in a particular direction. So we would call it a scalar field. As opposed to those electric fields that influence charges in a particular direction, or gravitational fields that influence masses in a particular direction. Now, these fields, they're regions in which an electric force could be experienced by a charge, but the field is there whether we have the force being experienced or not. The field is there as long as we have a producer, a positive producer or a negative producer. If we put something here to experience that, then there would be a force. But if we don't, the field is still there. Just like we got our board marker above the surface of the Earth, if we take that board marker away, the gravitational field is still there, just not causing a force. A force, on the other hand, requires both the producer and something to experience it. You can have, let's make it a negative producer this time. That causes its own field. But there won't be a force until there's something out here to experience that field. So, field is there no matter what, as long as we have something to cause it. The force is only there, the push or the pull is only there if there's something to cause the push or the pull, and there's something to be pushed or pulled. We got to have a producer and an experiencer. Let's talk about the direction of the electric field now. It's a vector field. We said just a minute ago that along with a gravitational field, an electric field is a vector field. So there has to be a direction associated with it. Therefore, we should define the direction. We would define the direction of a gravitational field as, well, it would be the way that a mass would move when placed in the field. The gravitational field would point downward toward the Earth because when I drop this board marker, it moves downward toward the Earth. The definition of the direction of the electric field is a little bit trickier, though, because there's two types of producers and there's two types of experiencers. Unlike mass, there's only one type. We're going to define the direction of the electric field. The first way is the way that a positive particle would move if placed in the field. Doesn't mean we have to have one in the field, but if we did put one in the field, this is the way it would move. It's kind of like saying gravitational field is the way that this board marker would move if I placed it in the gravitational field. Well, if I place that board marker in the field, it's going to move downward. If I don't place it in the field is still downward because that's the way that the board marker would move if it was there. This is the way that a positive particle would move if it was in the electric field. The second way we define it is in terms of the producer. It's away from a positive producer, and it's going to be toward a negative producer. So if you use gravity in the Earth analogy again for a moment here, we would say the gravitational field points toward the Earth, toward the producer. Would never point away from anything because gravity is always attractive. Now, got a couple diagrams here. The line in the middle just shows that they're supposed to be separate, completely separate, independent diagrams here. We're going to make one of these charges positive. We're going to make one of these charges negative. Let's look at these two definitions of the direction of the electric field and try to understand it a little bit better with these diagrams here. Let's put a positive charge right here. Let's put a negative charge right here. If we look at the first definition, the way that a positive particle would move if placed in the field, then we would say the field must point this way because the positive charge would be repelled by the positive producer. It would move outwards. Now, I don't have a positive particle right here, but if I did, it would also move outwards. And I don't have one right here, but if I did, it would also move outwards. And here, and here, and here, and here, and so on. The positive particle would move outwards away from this positive producer no matter where I put it, including right here. Which way would the negative particle move at that point? It would move towards it. So the electric force on the negative particle would be towards it. But remember, we're not defining the direction of the field as the way that a negative particle would move, even if there's one there. We're defining it as the way that a positive particle would move if a positive particle was there. So You may have a positive, it's going to move away from the producer. You may have a negative, it's going to move toward the producer. You may have nothing surrounding it. In all three cases, the field will point away from the positive because that's the way that a positive charge would move if it was there. Now let's look at the negative. Once again, we're going to put a little positive experiencer out here, a little negative experiencer up here. Which way is that positive going to move as a result of that negative producer? It's going to be attracted to it, right? So it's going to move towards it. Well, if I put a positive charge up here somewhere, it would move towards it. And so on. Doesn't mean I need a positive experiencer in any one of those places. I'm just saying that if I put one there, that's the way that it would move. Which way would the negative move? It'd be repelled by the negative producer, so it would go this way. But that's not the way we define the field. We define it as the way the positive particle would move. So the electric force on the negative is in green, but the field, whether we've got a positive particle there or a negative particle there or no particles there, the field is represented by the red. Away from positive and toward the negative. All right, I want to draw a few electric field diagrams. The first one, we have two charges here separated, so they're not influencing one another whatsoever. One of them is going to be positive, one is going to be negative. We already did this one, right? The positive producer causes an electric field that goes away from it. The negative producer causes an electric field that points towards it. And we know that's the case because that's the way that a positive experiencer would move when placed in that field. Now, let's take away that little line that's separating the positive from the negative. These two charges are now close enough to each other to interact with each other. In the last diagram, we had that line drawn in between them showing that like they're independent of one another. They're far enough apart where they're not really going to affect each other. Now they're close enough together that they do affect each other. Let's draw the field lines surrounding these two charges now. Well, firstly, around the positive, it would look something like this, just like it looked in the last one. And surrounding the negative, it would look like this, just like it did in the last one. But if they're close enough to interact with each other, then the field lines that are in between the positive and negative actually join up like this. Similarly, if we happen to have two positives nearby each other so that they interact with each other, the field lines would look something like this. Away from the positive, but in between there, they don't join up at all. Rather, they repel each other like this. When field lines join together like they do in the first diagram, we always have a force of attraction. If field lines don't join up, if they repel each other like they do in the second diagram, then we always have a force of repulsion. Now in these two diagrams, like you can clearly see that we've got attraction and repulsion, but sometimes the diagrams get a little bit more complicated. Sometimes you may see a diagram on a quiz or a test or an assignment where you've got 3 charges or 4 charges or some different shape charge, and the field lines, they draw the field lines, but they're not recognizable to you. You haven't seen a diagram like that before, and you have to determine whether they attract or repel. If you've never seen the diagram before, don't sweat that. Don't lose sleep over that. Look at the field lines. If they join up, regardless of what the shape is, regardless of how complicated they look, if they join up with each other, then it's an attractive force. If they don't join up, then it's a repulsive force and it's attraction. All right. This diagram that you see here represents an electric field pointing downward. This electric field could be caused by a big positive up here, field points away from positive, or it could be caused by a big negative down here toward the negative, or it could be caused by a positive and a negative, or it could be caused by two charged plates or something like that. It doesn't really matter. Okay? We don't really care what it's caused by right now. I just want to look at what effect it has, not what it's caused by. The first thing I want to look at here is a positively charged particle at rest. What's going to happen to that positively charged particle at rest? Where's it going to go? Does it experience a force? If so, which direction? And where does the movement go?
It will experience the force. It'll be a
Good. Yep. There's a downward force. And the reason there's a downward force is because positive particles experience a force in the direction of the electric field. That's the way to define the direction of the electric field, right? The way that a positive would move if placed in the field. If the field is downward, then the force has to be downward on it. What if I put a negative particle in that field with a speed of 0 meters per second at rest, 0 meters per second? Which direction would the electric force be on that one? Negatives would, if positives experience a force with the field, then negatives would experience a force, yeah, against the field. So the electric force on this one would be upwards, opposite to the direction of the field. Yep.
So is that like why
No, that comes back to that question on the check and reflect questions that we had earlier on, where you've got positives attracting negatives, but you've also got negatives repelling negatives at the same time. So it's a balance of forces, not so much the field there. Okay, let's do another one. This time, let's make the positive charge moving to the right. It's moving to the right. I don't know how fast. Let's make it 100 meters per second. Whatever. It doesn't really matter how fast it is. It's moving to the right. Does it experience a force? Yes, it does. Which way? Yep. No, it does not experience a force diagonal. Downward. A positive particle experiences a force in the direction of the field. Okay, the force is downward. Yeah? Okay, so you're answering another question then. Not which way is the force. The force is always with the field for a positive. If it was a negative particle, then we do the same thing except we draw it upwards, right? The force is always with the field or against the field, always. Now, your question is, which way would it go? It would end up going in between, right? It would end up going actually something like this. Does anybody know? This is a great question. Does anybody know what the shape of that path would be called? Think back to something that we did in Physics 20. It's remarkably like this. Shiva? No. Good guess, but it's not an ellipse. An arc? No. It's acceleration, yeah, but that's not a shape. That's the motion that it exhibits in one dimension. It's a parabola. You remember in projectile motion, you had a gravitational field pointing downwards, and you threw a rock in that, and it followed a parabolic path? This is exactly the same thing, except we're replacing the gravitational field with an electric field. If you throw a rock in a gravitational field and it follows a parabola, well, then you throw a positive particle in an electric field, it's going to follow a parabola. Now, if you put a negative particle in there, it would also follow a parabola, but it wouldn't be a downward parabola like this. It would be a parabola curving upwards, right? But it would still be like projectile motion. It would still be the same thing, except it would look different because the parabola curving upwards. All right, I want to give you just a little bit of math here and do one example question, then we're going to be done for the day, okay? 3 equations that you saw back last year in your gravity unit. First one, we've used this, we've seen this already in this unit. This is the equation for gravitational force. The gravitational force that exists between two charged particles. There is an analogous equation to this in electricity, and it is F is equal to K Q1 Q2 over R squared. Gravitational force, the electric force. Two masses, two charges. I don't know if you remember this, but last year we also did an equation that described the gravitational field. That's the second equation. It's the gravitational field that's caused by something. In other words, the producer equation. Call it the producer equation for gravitational fields. In other words, if we know something about the thing that causes the field, then we can use this equation. The Earth causes a gravitational field. If we have data about the Earth, then we can find the gravitational field caused by the Earth with this equation. Anybody want to tell me what the analogous equation with electricity would be? If G is equal to Gm over R squared, then electric field, which is E with the arrow over it, don't forget that arrow because you don't want to get it mixed up with energy, would be equal to what, Chase? Good. KQ over R squared. Q would be the charge of the producer, whatever it is that's causing the field. And that's going to be in coulombs. And R would be the distance from the center of the producer. So if you're trying to find the field strength 10 meters from the center of a producer, then R would be 10 meters. And finally, this last equation was the experiencer equation. For gravitational fields. In other words, if you had information about what experienced the field, the board marker in the analogy that we were using earlier, you know information about the board marker, then you would use the experiencer equation. Well, the experiencer equation for electric fields would be F over Q. It's F over M for gravity. It's going to be F over Q for electric. Now, if it's up to me, I put absolute value signs around those, although on your data sheet it doesn't have them. It's not a big deal. The vector sign is a big deal. The absolute value sign is not so much. F would be the force experienced, the electric force experienced, and that would be measured in newtons. And Q would be the charge of the experiencer, not the charge of the producer. What do you think the units would be? There's one equation that gets you the units pretty easily here. Yeah. Yeah, we're going to say newtons per coulomb, right? Newtons over coulombs. Now, you could derive those units from this equation as well. It's just a little bit harder, that's all. Let's do one example, and then we'll call it a day. Example number one on the handout that you got a few minutes ago. It says, determine the electric field strength and direction 50 centimeters to the right of a sphere that has a negative charge of 25 microcoulombs. We're going to circle these two things because those are non-standard units, and we don't want to forget to convert those to the standard units of meters and coulombs later on. What do you have here? Is this a producer or an experiencer? I got data about something, right? Does that data reflect the producer or the experiencer? What causes the field or feels the field? It would be the producer, yeah. It's not the experiencer. Here's why. If you have a negative charge right here that's 25 microcoulombs, and you're trying to find the field strength out here, okay, this charge cannot experience the field strength right here, 50 centimeters away. It's not there. To experience something, you need to be there to experience it. If the weather is plus 5 degrees outside, to experience that, you need to be outside where the weather is 5 degrees. This charge is not at this point. It can't be experiencing the field there, therefore it must be producing it. So knowing that, we're going to write down some givens here. The charge is the charge of the producer, and it's 25.0 times 10 to the minus 6 coulombs, because it's microcoulombs. The distance from the center of the producer would be 0.500 meters, because it's 50 centimeters. And we want to find E. We're going to use the producer equation. E is equal to KQ over R squared. Let me just finish this up quickly here. K is 8.99 times 10 to the 9. Q is 25 times 10 to the minus 6. We can make that 2.5 times 10 to the minus 5, but I think it's easier just to leave it this way. And R is 0.500 meters. We're going to square that. Let's do the math on that one. 8.99 times 10 to the 9 times 25 times 10 to the minus 6 divided by 0.5 squared gives us a value of 8.99 times 10 to the 5. What do we say the units were? Right, newtons per coulomb. What about the direction? What about the direction? Here's my negative producer. I'm trying to find the field strength right here to the right of the negative producer. Which direction is it? To the left. The field always points toward a negative producer. So the field would be to the left there. Does that make sense? All right.